Welcome class to our video notes lesson on section 4.9, where we are going to be introduced to the notation and how to evaluate what are called logarithms. So what I want you to keep in mind throughout this video is that a logarithm equals an exponent. A logarithm is a type of function that basically puts all the emphasis on the exponent in an exponential expression. So the notation for a logarithm is this. You have the first three letters of the word logarithm, L-O-G. You have a subscript, which we often put with a lowercase b. You have the input, which we are going to write here as a, and then you have the output, the result of what the log equals, which here we'll call x. So what this notation means is that if I were to take this base b right here and raise it to this power of x, then the result of that would equal a. So you can see that the output of the log is equal to the exponent. The log equals the exponent. The thing that was inside the log is the result. We call it the answer. What you get after you take that base b and raise it to the power of x. So the other way to think of this is our three letters, L-O-G, our subscript, which would be the base of our exponential expression. The inside of the log is the answer, or the result of the exponential expression. And the output of the log is the exponent, or the power from the exponential expression. So this version here, the one with the log, is called the logarithmic form. And the one over here written with a base b and a power of x, we call that exponential form. But these two expressions are saying the same thing. They are saying that if you were to take a base b, raise it to a power of x, the outcome or the answer to that would equal a. Both of these are saying the same thing, but the logarithmic expression is placing all the emphasis on the exponent. The base has sort of been demoted as a subscript, and the output is the exponent. So it's kind of popping out the exponents. So when we are evaluating logarithmic expressions that look like this, there's a question we have to kind of answer in our head. And that question is, what exponent would I have to raise b to get a? That's the question we ask. What is the exponent? Because that's what the log equals. The log equals the exponent. So why don't we start over here practicing just kind of going back and forth between these two forms in example 1. So in example 1, I can see from this exponential expression that my base is equal to 5. 5 is the thing that I'm raising to a power, so that's my base. I can see that my power, or my exponent, is 3. So I'm raising 5 to the power of 3. And then I can see that when I do that, when I do 5 times 5 times 5, the answer is 125. So when you write a logarithmic expression, the base goes as your subscript. So my base of 5 would be my subscript. It's kind of been demoted. The answer to the exponential expression goes inside the log. So the 125 goes inside. And then the number that the log spits out is the exponent. So whatever the exponent is, that's what the log equals. The log equals the exponent. In number 2, I can see that my base is 49. It's the number being raised to the power. I can see that my exponent is a fraction of 1/2. So as a quick reminder, that's a square root, right? That was our last lesson. A power of 1/2 equals a square root. And so the square root of 49 is 7. So my answer, or my result to that exponential expression, was 7. So when I put this in the places where they go for a log expression, the 49 would become my subscript because that was my base. 7 would become my input because that was the answer to the exponential expression. And my output for the log is the exponent. Because remember, the log equals the exponent. 1/2 is the exponent that I would have to raise 49 to get 7. Why don't you guys try number 3? So looking at the way this is written, I can see that my base would be 2, since that's the number being raised to the power of 6. So the power was 6, so that's my exponent. And when I raise 2 to the power of 6, in other words, when I multiply it to itself 6 times, the result or the answer to that is 64. So that's the number that goes inside the log, the result, right? The base becomes a subscript, and then the log equals the exponent. So the exponent of 6 is the output or the result of the log. Now in example 4, you might be wondering what this letter is. E is another example of when we use a letter to represent an irrational number. E is actually known as Euler's number. Of course, you pronounce it Euler, but it's spelled E-U-L-E-R. Euler's number. So the E for the first letter of his name. And the value of it is approximately 2.72. And this number we're going to learn a little bit more about in later units, but we sometimes refer to it as the natural base because it tends to be the base in exponential functions representing natural types of growth or decay, things happening in nature or just a sort of natural process. So this E right here is referring to this number. Of course, this is the rounded version. We use E when we want to use the exact version of this number. And most of your scientific calculators already have this number programmed in. So you can kind of take a look and see if it's on your calculator. You can punch it in and see the other decimal places. But if you round it, it's approximately 2.72. So anyways, that'll be our base in example 4 here. The exponent is 0, and the result, or the answer of raising e to the power of 0 is 1. In fact, any number, including an irrational number, raised to the power of 0 is equal to 1. So, if I write it in logarithmic form, e would be my subscript. 1 would go inside, because that's the answer to the exponential equation, and then the log equals the exponent. Now, there's one more thing you do need to realize about this one, and that is because this number e is considered to be our natural base and occurs quite often in natural types of exponential growth or decay. This is a very common logarithm, and so it has its own abbreviation. So whenever you have a log base e, we think of that as the natural log, because it's the log of the natural base. And so the Latin for that was Logarithmus naturalis. ln is the Latin version of natural log, and ln means the same thing as log base e. So this expression here would actually be written as ln of 1 equals 0. So the log equaled the exponent, and ln is equivalent to log base e. So you might look at your scientific calculator and notice that you have both an log button and an ln button. The ln button is referring to a log that has a base of e. Okay, so now in example 5, we are going to go the other way around. We have these expressions that are logarithmic, and we want to convert them into their exponential forms. So we have to remember what each piece is. So the subscript, if you remember, is the base of the exponential expression. The number inside is representing the answer to the exponential expression, and the log equals the exponent. So the output of the log would be the exponent of your exponential equation. So rewriting this in exponential form would now put the emphasis back on the base. So that's the large number now, and now the exponent is this little tiny superscript, right? 9 squared, and then the answer to that is 81. So that would be the exponential form there. Why don't you guys try number 6? So in this logarithmic expression, my subscript was 7. So that would be my base of the exponential expression. The number inside was 343, so that's the answer to the exponential expression. And the log equaled 3, which is the exponent of my exponential expression. So then putting everything where they go in an exponential expression, I've got a base of 7 raised to a power of 3 equaling 343. Now in number 7, I can see my subscript is 6, so that would be my base. And the inside of the log is the 1 over 1,296. And the exponent for that, because that was what the log equals the exponent, is -4. So the exponential version of that would have my base as 6. My exponent now is the little superscript, and then that equals 1 over 1,296. And again, just a quick review, that was our rule of exponents we recently reviewed. But a negative exponent, what that'll do is it'll take the reciprocal of that expression. And so it'll be 1 divided by 6 to the 4th. And 6 to the 4th is equal to 1,296. So this here is our exponential expression. So now we're ready to start evaluating some log expressions. And there's varying levels of difficulty with these. The first one we're going to start with is one of the easier ones. And we're looking for an exponent, because remember, the log equals the exponent. So I know the base is 3. I know the answer to my exponential expression is 81. What I'm trying to determine is what the exponent is. So maybe I can think of just calling it x. And so what I'm trying to do is figure out what x would be in this expression. 3 raised to what power equals 81? So you might recall from some of these simplifying radical problems we were doing, if you do 3 times 3 times 3 times 3, that'll give you 9 and 9, which is equal to 81. So I need 4 factors of 3 to get to 81. So my exponent here would have to be 4. So what that means is that this log expression is equal to 4. Log base 3 of 81, that whole expression is equal to the number 4, because 3 to the 4th power is equal to 81. The log equals the exponent. So the answer is 4. Now in number 9, this is one that I would consider to be a medium level. It's not the hardest type, but it is definitely a little harder than number 8, because I'm dealing with a reciprocal as my answer. So I can see that my base is 2, and my answer is a fraction, some kind of reciprocal. So for my exponent, which is what I'm trying to find, so maybe we'll call this x for now, right? And think of this as 2 to what power is equal to this fraction. Trying to find the exponent. Well, I know it's got to be a negative number, because that's what has to happen to flip my base over. I need to get a reciprocal of my base. So maybe I could just kind of focus on the 32. We've been working with that number a lot lately as well, simplifying radicals, and we've come to find out that 32 is what you get when you multiply 2 to itself 5 times. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th power would give me 32. So if I make that power negative, 2 to the negative 5th, then that would take the reciprocal. That would do 1 over 2 to the 5th, which is 1 over 32, which is what I have here. So I now know that my exponent would have to be -5. So this log would have to equal -5. So log base 2 of 1 over 32 is equal to a negative number, and it has to be -5, so that when I take the reciprocal, I end up with a 32 in my denominator. The log is the exponent, so this log expression equals -5. Now number 10, again, I consider to be one of the easier ones. Not easy, but just easier compared to the other ones. Why don't you guys try this one? So the answer is 4. And that is because that is the power you would have to raise 5 to get 625. And that's, of course, what this log expression is looking for. It's looking for the exponent. The log equals the exponent. So your job is to try to figure out how many times do you have to multiply 5 to itself to get all the way to 625. And it turns out you need to multiply it 4 times. Now in number 11, this is the kind that I consider to be the hardest, because you have a base that's larger than your answer. So the base of 64 is greater than the answer, which was 4. So that could only mean one thing. That means 4 is a root of 64. That means 4 raised to a certain power is 64, and therefore if I take a root of 64, I get down to 4. So when I'm raising my 64 to the power of x, 64 is the base here. 4 is not the base. 4 is the answer. So I'm raising 64 to the power of x and somehow getting 4. That means that my exponent, which we're trying to figure out what it equals, must be a fraction. And it must be a fraction that's less than 1. Because 64 to the first power would equal 64. So the only way I could get it to equal something less than 64 is if this power was less than 1. Now I don't want my power to be negative. If my power was negative, then I'd have a reciprocal. I'd have 1 over something. So this is not a reciprocal. It's just smaller than 64. So I'm looking for a rational exponent that would represent a root of 64. Okay, so what I want you to think about is how many times would I have to multiply 4 to itself to equal 64? Let's kind of just start there. 4 to what power equals 64? In fact, I think it's only 3 because 4 times 4 would be 16, and then if you multiply 16 times 4, you get 64. So 4 to the third power is equal to 64, and then that implies that 64 to the power of 1/3 is equal to 4, right? The cube root of 64 is 4 because 4 to the third power is 64. Okay, so that's what my exponent needs to be. It needs to be a 1/3 power because a 1/3 power represents a third root. So my answer here is 1/3. So the log base 64 of 4 is equal to that exponent of 1/3. So I always feel like those are a little bit trickier, trying to figure out what root of the base would equal the answer. And in this case, it was a third root, so my exponent had to be a rational exponent. It had to be the fraction 1/3 to represent a third root, and so that was the value of my logarithm. Now let's take another look at this natural log again. We call it the natural log. So remember, that's the log that is a base of e. So I can rewrite this as a log base e of e to the power of 10. And I'm trying to figure out what exponent I would have to raise this base e to get e to the 10th. So e is my base raised to my exponent of x equals my result of e to the 10th. And I'm trying to figure out what that exponent would have to be. Well, I hope it's kind of obvious from writing it this way that if I want to get the result of e raised to the power of 10, then I need to raise e to the power of 10, right? E to the power of 10 equals e to the power of 10. Now I know this probably looks so strange to you because you have to sort of remember e is a number. It is written here as a letter, but it's representing this number. And so you would have to raise that number to the power of 10 to equal the result of that number to the power of 10. So in this instance, my exponent is 10. One thing you can also remember here is that because this is a base of e, and this is a base of e, then whatever the exponent is of my answer would have to be the exponent, would have to be what the log equals. So in a sense, these sort of cancel each other out and just leave you with the exponent. Now in number 13, this is the natural log of 1. We actually looked at this one earlier. Let's just take a peek back. That was our number 4. And so we know it's going to equal 0 because of what we had done here. But let's pretend that we hadn't looked at that yet. And we are trying to figure out what it equals. So again, we're going to remember that natural log is equal to a log base e. So this is a log base e of 1 that I'm trying to figure out what it equals. So I would rewrite this as e to what power equals 1. And the power is unknown. So this is where you have to just remember, and this is true for any number, including this irrational number, but any number raised to the power of 0 would equal 1. That's true for any base, not just e. So that is my answer. That's what the log equals. The log equals the exponent. So my exponent was 0, so ln of 1 is 0. E to the power of 0 equals 1. Now in number 14, we have a negative result on the inside. So this is actually undefined, does not exist. But I want to explain to you why. So I want to back up to the beginning of this outline for just a moment and give you some qualifications for this base b. In these logarithm expressions, we have to understand that b is not equal to 1 because 1 raised to any power is equal to 1. So when your base is 1, that's not really an exponential expression, so my base can't be 1. And my base has to be greater than 0. So that means that my base is never negative. So by definition of these logs, this subscript here is always a positive number. And in this case, it's 2. So I'm trying to figure out 2 raised to what power would equal negative 8. But because my base is positive, there's no way that I could multiply it to itself, which is also a positive number, and end up with a negative result. 2 to the third power would be positive 8. 2 to the negative third power, so maybe you think, oh, the exponent's negative. But no, the negative exponent doesn't make the result negative, it just gives you a reciprocal. It would just be 1 over 8. It would not be negative 8. So there's just no exponent that you could raise 2 to get a negative value. It just can't happen. So another thing we have to understand about logarithmic expressions is that their domain, which represents the inputs, things you're allowed to plug inside, the domain can only be positive. So I'm putting a here because that's what we used earlier, right? We had log base b of a. That input, that answer, right? The answer to an exponential expression can never be negative. It has to always be positive. So that's kind of a domain restriction on these logs. So we cannot plug in a negative to a log, and we cannot evaluate the log of a negative. If you tried plugging it in your calculator, you would get an error message, error domain, because it would be saying you can't plug in a negative. That's breaking the domain rules. Last, but definitely not least in this outline, we're going to learn how to use your calculators to go ahead and evaluate these logs. Now, most calculators do not let you plug in whatever base you want. Most calculators have only an LOG button or an LN button. Now, the LOG button is called the common log, and that is equal to a log of base 10. So when you hit that button on your calculator, what it's doing is it's finding a power of 10. It's saying 10 to this power would equal whatever that answer is. So you can convert logs to a base 10, or you can convert logs to a base e. So if you remember, the ln stands for natural log, which is a log base e. So if you're working with logs that are neither base 10 nor base e, like these examples here, what you can use is this thing called the change of base formula. So the change of base formula looks like this. Let's say you have a log of a certain base m, we'll call it, and the inside is n. And let's say you want to change this base. You say, okay, I don't want base m anymore, so you want to change base m to be a base b. These are hypothetical numbers, right? So we're using letters to represent them. But the idea is we're changing from a base m to a base b. It's a fraction. And that fraction goes like this. Log of the new base b of the original input n divided by log base, new base b, of my old base m. You can plug that in instead, and it will tell you the value of this log. And you can use either log or ln. Either way is fine, and I'm going to show you actually both in a minute. Let me just write down for you, though, how this works. So in this case, m, if you will, right, the old base, is 4. And on my calculator, I don't have a base 4, I only have base 10. And I want to convert to base 10. So I want to switch over to a base 10. This would be my old input n. I would do it like this. I would say, well, I want a base 10. So I have the 22 in there, because that's the formula, puts the old input in the top one. And then I'm going to divide that by log base 10 of the old base. So in this case, my old base is 4, or my original base is 4. So I can find log base 4 of 22 by doing log of 22 divided by log of 4. One other comment on this is that because the log base 10 is so common, actually we don't write the subscript. So a log with no subscript is a base 10. So for example, if you had log of 100 equals what, you can see there's no subscript there, it's empty. But it's like kind of like a square root. When you don't see an index on a root, we know it's a square root. It's like the default. Well, base 10 is the default for log. So we just understand that that's a base 10, and we go, oh, this would equal 2. Because 10 to the power of 2 is 100. So you can try it right now on your calculator. If you type in log of 100, the result it'll pop out for you is 2, because the base of that log, though it's not written, is 10. So go ahead and plug this on your calculators, and let's see what we get. Okay, so let me kind of show you how this works on a calculator. Of course, here I'm looking at the TI-84 graphing calculator, but this is the buttons I'm going to press you can also find on a regular scientific calculator. But basically what I'm wanting to use is this LOG button. So this LOG button is a log of base 10. You can see right underneath is the LN, which is log base E. They are usually found near each other in a graphing or scientific calculator. And I want to type in the log base 10 of 22. Close the parenthesis. So oftentimes you'll find parenthesis buttons on scientific calculators, so you can say that that's what's going inside the log, right? Every log needs an input. And then I'm going to divide that by, so I just click the division, log base 10 of my old base, which is 4. And I want you to know that this is finding log base 4 of 22, but using the log buttons provided by our calculators. So I'll hit enter, and then it gives us our decimal value. And so that's what we can understand the log base 4 of 22 to be. So you can even see here, if I were to raise 4 to the power of 2.2297, I'm going to type in all these decimals because otherwise it's like an approximation. If I type that in, I should get a number that's close to 22, right? This is pretty much 22 if you round it up. So that's what this is giving me. This is giving me the power that I'd have to raise 4 to equal 22. But because I don't have a log base 4 as these buttons, I'm using the change of base formula, which allowed me to use a base 10 log to calculate a base 4 log. Now you can change bases to any base. So I could have also used a natural log. This is a base E, but I could follow the same change of base formula. So put my new log with my new base of my old input, divide that by my new log of my new base of my old base. And it'll give me that same power, 2.2297-ish if I round it. So either one, the LOG or the LN button will work. And what it effectively calculated for me here is the log base 4 of 22. Okay, so we just saw from that demonstration that our log is approximately 2.2297 if I round to the 4th place. It's good not to round too much because the more we round, the more accuracy we lose. So going to the 3rd or 4th decimal place is ideal. We also saw that you can get that same number by using ln in our change of base formula. So why don't you guys try numbers 16 and 17? Okay, so first we kind of recognize our m in this case is 5, and we're switching over to a base of 10. and our input is 152. So if I want to use a log base 10 to determine the value of this, so by the way, these are approximations for this log, but I'm using the change of base to get that. I would do a log of the inside divided by a log of the old base, and I get about 3.1215. Notice again, you can use the natural log as well, because that's another one that's on most calculators, and it would get you the same decimal. Now notice that the value here is just a little bit greater than 3, because if you remember, 5 to the third power is 125. And this number here is just a little bit bigger than 125, so the exponent that I would have to raise 5 to would be a little bit bigger than 125. It would be 152. You can check that, by the way, on your calculator. 5 to this power should equal something close to 152, which is just a tad bigger than 125 because the exponent was just a tad bigger than 3. Now in number 17, we ended up with this decimal. So again, I had an old base of 11 and my input was 3. So to use my change of base formula, I did log base 10 of the old input 3 divided by log base 10 of my old base 11, and I got about 0.4582, so just right around a half. And then you can also use the natural log, right? ln of 3 over ln of 11, it'll get you the same value. So notice that this value is less than 1. So the 0.4582 is less than 1. The reason for that is because 3 is less than 11. 11 to the first power would equal 11. So if I'm trying to get it down to 3, this power here would have to be smaller than 1. So it turns out that if you raise 11 to the 0.4582 power, it'll be approximately 3. Well, that concludes our video notes on logarithmic form. Of course, this video was just meant to sort of expose you to the notation and help you understand how to evaluate them. There will be a lot more details about this type of function and how it works and what it's for coming up in our next unit. So stay tuned, and I'll see you in class.